Okay, so welcome back again. Today is our 32nd class. We are going to talk about logarithmic functions. This is a brand new category of functions that we have not discussed at all this semester. It's possible some of you have never seen them before, but maybe some of you have seen them and it's a little bit fuzzy. But we're going to jump in as if we have no prior experience on log functions. We've got one more day on log functions Wednesday. Coming up on Friday is our review day for the test, which is on Monday. Okay. And it is not too early to start studying for the test, which is 1 week from today. And as usual, near the back of this packet, sample test problems for you to practice with, okay? All right, so we did have our third quiz, which I've just handed back. If you came in late, I'll give it to you in just a little bit. And that's all you're working on right now is just thinking about the test. We will have one more project coming up, one more quiz coming up in the last few weeks of the semester. Questions on any of that? Okay, then let's take a look at this one-page handout from your tables. So hopefully this is the equation that, that you guys came up with. 7,000 equals 5,000 times 1 plus 0.02 over 12, all raised to the 12t. If we could somehow find the value of t that makes this equation true, we will know how long it takes for $5,000 to grow to $7,000 when we have 2% interest compounded monthly. The difficulty is that the variable, the t, is up in the exponent. And right now we have no way to solve for a variable that's up in the exponent. And so that's what the new tool is that we are going to play with today. It's going to be able to solve this equation, okay? All right, so put this equation on the back burner. And we're going to come down and jump in here on this graph. So I've put some lines through, you can, but you don't need to. All we need to know is that the graph of this function, f of x equals 2 to the x, is pictured. Remember, that's an exponential growth function. Okay, and this function has an inverse function. Do you guys remember stuff about inverse functions? The idea here is that for an inverse function needs to pass to have an inverse that's a function, the original needs to pass the horizontal line test. You guys remember that? And because there's no horizontal line that hits the graph more than once, yes, this thing has an inverse. Now, I don't know what the inverse function is. I'm trying to solve, I'm trying to figure out what, you guys remember this idea? Just changing the f of x to a y, and then we swap the x and the y, you remember that? So I'm swapping the x and the y, and I'm trying to solve this equation for what letter? For y. But I don't know how to solve that for y. So I don't know what the inverse function is. I'm just going to give it a generic name for right now. We're going to call the letter g the inverse function for that function right there. I don't have a formula yet, but I'm just giving it a name. For sure, there's some inverse function out there. Right now, we're on a one-page handout. Giovanni, okay, right there. Okay. So let's talk about this. F of 3 is equal to 2 cubed. Let's make sure we see that point. That's right here. You guys agree? 3 and then 2 to the 3, 3 comma 8. So what happens with the x and y when you go to an inverse function? Swap, right? That's the first thing you do when you go to an inverse is you swap the x and the y. So what that means is that for g, this unknown inverse function, instead of, what number am I going to plug in? I'm going to plug in 8. I'm going to call it 2 cubed, but yes, 8. And what's the answer? What's the output? Is 3, right? Just swapping the x and the y. Likewise, since f of 5 is equal to 2 to the 5th, g of 2 to the 5th equals 5. Everyone agree? Just swap the x and the y. Same idea down here, but I gave you one more blank. F of negative 4 is what? I'm looking for we're plugging negative 4 into our function. F of negative 4 is 2 to the negative 4, right? Not even doing anything with that, just copying it 2 to the negative 4. And therefore, when I go to the inverse function, g of 2 to the negative 4 equals negative 4. Okay, so what we see here is that the g function, again, I don't know what it is, it's just named, but it takes whatever power is up there and it just lifts it off, right? 3 comes to 3, 5 comes to 5, -4 comes to -4. So we're going to call g the liftoff function. It just takes whatever power you have, lifts it off. That's your answer. So how much is g of 5 to the 4th by lifting off the power is 4. Really easy, right? Just lift off the power. G of 3 to the 2/7 is 2/7. And g of 9 to the -2, -2. Easiest questions all semester. G of 4 to the -1, -1. So g is the liftoff function. Okay, let's flip to the back. And let's take a look at g of 9. Now, 9 at the moment is not written in a nice power form. It's not written in exponential form. So 9 is really what to the what? It's really 3 to the 2nd power, right? And now that I've got the input written in liftoffable form, what is g of 3 squared? 2, right? Just lift off the power. Okay, let's take a look at number 7. G of 16. Again, I need to write it in a certain power form. So it's really 4 squared. So therefore 2, right? Is there any other way to think of 16 as a power? 2 to the 4, isn't it? 2, 4, 8, 16. So then what's the answer here? Lifting off the power is 4. Well, that's very problematic because I can't have, on the one hand, g of 16 is 2, but on the other hand, g of 16 is 4, right? That's not a function. So what we're going to do is we're going to add a little bit of notation here where I'm going to give you information that tells you what the base is. If I want you to write 16 as 4 to a power, I'm going to put a little 4 right down there, and that's going to be your clue. Oh, he wants me to think of 16 as being 4 to some power. And so a little 4 down there, and that's how you know to put 4 to the 2. But down here, what was the base? Was 2. And so if I want you to think of 16 as being 2 to something, I got to put a little 2 down there, okay? And so these are really different functions. Even though they're both g of 16, one of them is g base 4, and the other one is g base 2. Good? Okay, so I think we can now fill in the blanks here. We've sort of done a bunch of this already. So g base 2 of 16 means g base 2 of, how do I write 16 now? Is 2 to the 4. And then g is the liftoff function, so the answer is 4. That's good. Or we could come down here and say g base 4 of 16 means 4 squared. And then g is the liftoff function, and we get 2. Okay, the last one, g base a half. This one's not as easy, so we're going to do some scratch work on the side. What I know is that it's supposed to be, what am I supposed to write here? I have to write a half, and then I'm just going to put like a box. I got to figure out what goes in there, right? That's good. So what I'm after is 1/2 raised to some box is supposed to equal what magic number? It's supposed to be 16. I'm trying to rewrite it as 16 as 1/2 to something. And so just kind of having a little miracle here. Aaron, what did you say? Aaron says -4. You guys remember a negative power does what to the fraction? It flips it. And so when you flip, the 1/2 becomes 2 to the +4, which is absolutely right in 16. So then we'll put that -4 up in our box. So what is g base a half of 16? Is -4, just lift off the power, okay? Okay, so this is all groovy. Let's see if we can generalize that last example to something like this. G base b of x. And so I'm giving you hardly any information here, but if we can just kind of abstract the last example we did, we should have a generic formula that we're working with here. Okay, what that means is that I'm trying to write x as what to the what? As what number? Or what? As b to something. That's what I'm after. If I could somehow rewrite this x as being b raised to some power. Okay, how about we just give this a name? I'm going to call it y, just so that I can be a little more concrete. Where does that y go in this other equation? It's in the box. And so I recognize this is a leap right here. That's the most abstract thing up on the board by far, but it is just an example like the one we did with this 1/2 and the 16. How did you want to rewrite 16? You wanted to write it as a half to some power, right? How do I want to write x? I want to write it as b to some power, b to some power, okay? All right, so here's the conclusion. What have we been calling g the whole time? It is the inverse of that 2 to the x, but what else? How have we been like enacting g? Like how, it's just lifting off, right? So g is the lift-off function. Lift off. Yeah, you like that. So that right there is the definition of the log. It is just lift off the power. And so for example, if we go to here, where are we going? Let's go up here. I'm just going to make something up. If I say this, log base 7 of 49 equals. So what that means is that I'm asking you to rewrite that 49. So I'm going to copy all of this. I'm really asking you to rewrite that 49 how? 7 to the second, right? You have to figure out what goes up there. And once you've figured out what goes up there, then you just lift off the power. So what is the answer here? 2 is correct. Log base 7 of 49 is 2. That's the answer to this problem. Pete, you like that, huh? You like that? Yeah, I like it. Yeah. Okay, and so I can give you another one here. Log base 5 of 125. I'm forcing you to rewrite that 125 as 5 to some power. What is it? 5 to the third is 3. Log base 5 of 125 is 3. And I can give you stuff that that we can't do as nicely, as easily as these, and that's okay. So I could say log base 4 of 10. What that means, I'm just going to give it a name here. I'm going to call it y. But what that means is I'm trying to take what and raise it to what power? I'm trying to take 4 and raise it to some power and make it equal to 10, right? That's the goal. Okay, there isn't a nice answer to this one. It does have an answer, right? There is some number that I can take 4 and raise it to. Let's see, so 4 to the first is 4, and 4 to the second is 16. So that means that the answer, the y, is definitely between 1 and 2. That's correct. But that's about all I can say. Is it something between 1 and 2? The calculator is going to help us and give us very accurate answers to how much that is. But whatever you get for y there, that's the value of log base 4 of 10. It is 1 point something for sure. Okay. Okay. So one other thing, and then you're going to start doing activity stuff. Actually, 2 other things. So first of all, these 2 guys right here, I want us to think of as being equivalent to each other. They are just different ways to write exactly the same thing. And so, the liftoff thing, it's a really nice idea. It's cute. It's got the letters L and O in it. But to be honest, I don't think about lifting off when I actually calculate logs of stuff. What I think of is this relationship between the log equation and then the corresponding exponential equation. And for me, it's just like a pattern. I just think of arrows here. I take whatever is down here, I raise it to that guy, then I cross the equal sign and I write an equal sign and I make it equal to that other guy. That's just the flow for how I envision this. So I don't actually think about liftoff, I just think about this pattern. And so if I gave you something like log base b of, I don't know, 8 equals something 512. That is not what I meant. 512 and 3. I just think about rewriting that as an exponential equation. What to the what equals what for these symbols? It's b raised to the third. You cross over the equals and you write an equals 512. Okay, and then you have to solve that equation. But solving that equation is, it's fairly straightforward. You just take a cube root of both sides, right? So for me, every log equation just goes hand in hand with some corresponding exponential equation, and it's just this pattern every time. Right? So you're welcome to think about liftoff, and you're welcome to think about rewriting as powers. For me, it's just those arrows. Okay, the only other thing I want to say is back here. So go back one page for me. I think we're on page 70 now. 70? Yeah. So there's the graph of 2 to the x. It's the function we were playing with in the beginning. And I want to know, what does the graph, so this is f of x equals 2 to the x. And what we're going to do is graph the inverse function. We're going to graph the inverse function. And so we graph the inverse function by just reversing x's and y's, right? And so, for example, we talked about the point, what am I doing here? 1, 2, 1, 2. This is kind of, wait. 2. Oh yeah, it's okay. All right, here we go. This point right here is what, comma what? 3, comma 8. And so when I go to the inverse function, what point am I plotting? 8, 3. So you plot the point 8 and 3. Let's just plot a couple more points. For example, this is the point right here, what? That's 0, 1, which goes to the point on the inverse function 1, 0, right there. And I'm going to do one more. This one's going to be really hard to see. I'm going to pick -4 here. Now, what does it look like the y is? It's really close to 0. But you know what it is. You know that the y is just 2 to the x. So 2 to the what in this case? 2 to the -4. And this is the one that Aaron shared with us earlier. 2 to the -4 is really 2 to the -4 is really 1 over 2 to the +4, right? And that's really 1 over 16. So what's the y coordinate there? 1/16, which, you know, to the naked eye is pretty darn close to 0. So that's fine. And then when I plot the corresponding inverse point, 1/16, comma, -4. So we go over 1/16, which is hardly anything at all, and then down to -4. So it is almost on top of the y-axis, but not quite. 1/16, -4. And so if we connect all 3 of those and many more dots that we didn't draw, we should get something that looks like this. It's really close to the y-axis there. It starts to curve up and do something like that. So this is the graph of g of x, which is the inverse of that guy, which we've now seen is the log function. Do you guys remember the symmetry that a function and its inverse that the graphs have? Yeah, it is 1-to-1. Symmetric over what? The origin, not quite. Over the what? It's not quite over the y-axis, no. How do I turn one graph into the other? And I need to flip the one graph over something to turn it into the other. What am I flipping over? It's over y equals x. You guys remember that? There's the line of symmetry right there. Y equals x. Flip the one graph and it lands on the other graph. That was just generally true about inverse functions. So what I want you to take away from that picture is that just like you are gaining comfort with the graphs of exponential functions, and if I just say graph 2 to the x, I'm hoping in your mind you start to be able to do this kind of thing. With some practice, I want the log graph to be another one in our growing toolkit of functions. So the log graph has just a couple of characteristics you need to remember. Gets really close to the y-axis but never touches it. It's increasing the whole time, but it's increasing slower and slower as you go up the graph, okay? All right, so what I want you to do, I'm gonna head to the activity. Let's come to this page right here. So this is page 71. Technically, the activity starts in the middle of the page, but I want you to start at the top of the page, okay? So just begin at the top of the page and let's see how far we can get.